We're asked to prove if that we add terms according to this pattern, where it's plus 5 every time, each term can be defined by 5n minus 3, where n is the number of terms that we're on in the sequence of numbers. We're asked to prove that that sum of terms is equal to just this expression over here. So what we can do is we can prove this by induction. And to prove something by induction, you start with a base case. We're going to say for n equals 1, there we go. For n equals 1, we have 2 equals 1 times 5, 1 minus 1 over 2. I've just plugged in n equals 1 into this formula, and n equals 1 into this formula. If we were to say n equals 2, then we wouldn't just be plugging 2 in here. We'd be doing 2 plus 7 equals 2, 5 times 2, etc. Okay, but for induction, you need a base case. You might as well make the base case nice and easy. Plug in n equals 1, and we can see that the left side is equal to the right side, because 5 times 1 is 5, 5 minus 1 is 4, 4 times 1 is 4, 4 divided by 2 is 2. It holds. These two sides are equal to each other. So that lets us do something cool. We can say that assume n equals k for all positive integers. And we seek to prove that these two sides when n equals k plus 1, the next term is equal to the current term. Like this. Okay? Everywhere where we had an n, I replaced it with k plus 1. Because we're assuming that it works for n equals k. We assume that it works right now. That's not enough to say that the proof is over, because all we've really proved is that it works for the first step. We want to prove that it works for the next step after that first step, because if that's true, then we can assume that it also works for the next step after that, and the next step after that. That's what the k plus 1 term does for us. So this is what we really need to do. We need to show that this side is equal to this side. To do that, you're going to want to expand this side a little bit, because we plugged in a k plus 1 term, right? And since these are going in order, since n just increases by 1 every time we go a step in the sequence of numbers, then we can expand this side. This is 2 plus 7 plus 12 plus ... plus 5 times k minus 3 plus 5 times k plus 1 minus 3. So I've taken the left side and I've rewritten it a little bit. In these ... dots, this could be, it depends on how big k is. There could be a ton of terms in here. We know that 5k minus 3 is going to be one of those terms, because if it ends at 5k plus 1, this is just backed up 1. This is like taking this k plus 1 and subtracting it by 1. So with a lot of these proofs by induction, that's one thing you've got to do, is you've got to rewrite it like this. And the reason why I did that is because now that lets me pull out a formula from our assumption that n equals k. We said that if n equals k, that this formula holds. That means the sum of these terms would equal k times 5k minus 1. In other words, these terms right here, the sum of these terms is going to be equal to this right side over here. It's going to be equal to k times 5k minus 1 over 2. Okay, so I just wrapped up this plus, 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 all these pluses together, the sum is equal to this because of our induction step. And then we haven't done anything with this term, so that's still over here. And our goal is to make it equal to this side when n equals k plus 1. In other words, the goal that we're trying to do when we keep rewriting the left side is we want it to be equal to k plus 1. And you don't have to write this in your proof. This is just here. I'll write it up here. We want it to be equal to k plus 1. I'm just plugging in k plus 1 everywhere where we see an n. This is what we're looking for. Because we're trying to prove that that these two sides equal each other when n equals k plus 1. So that's what we want to rewrite the left side to look like. We definitely don't have that yet, but let's get common denominators. So just multiply the top and the bottom by 2 here. And now I have common denominators. So I've got k times 5k minus 1 plus, I'll distribute this 2 to everything inside here. That's going to be 10k plus 1 minus 6, and that's all over 2. So we're getting close to our goal. We got it all over 2 like we want, but we have to rearrange and show that our numerator is equal to this up here. Let's see how we can do that. I guess we got to distribute everything here. We'll combine like terms after. So if you distribute the k here, that's 5k squared minus k plus 10k plus 10 minus 6. And then combining like terms. And I think this is factorable. 5 times 4 would make 20, and we got to find two numbers that multiply to be 20 but add it to be 9. So that's 5 and 4, right? So we got 5k squared plus 5k plus 4k plus 4 over 2. And then we factor the numerator by grouping. So if you do that, you can take out a 5k in the first two terms. You can take out a 4 from the last two terms. And then the last step of factoring by grouping is that both terms have a k plus 1 term. So you can take out k plus 1. And what we have left is 5k plus 4. And that's close. We've got the k plus 1. And we actually have this because if you were to distribute and simplify, this would be 5k plus 5 minus 1. So this is 5k plus 4 right here. This is 5k plus 4. So we've reached the end of the proof. We've taken the left side when we plugged in k plus 1, and we kept rewriting the left side until it was equal to the right side when we plugged in k plus 1 in for n. The proof is pretty much done. If you wanted to rewrite one last time, just make sure 5k plus 4, that's the same thing as what we have up here, 5 times k plus 1 minus 1. And so our proof is complete. We proved that the formula holds for the next term. If you assume it works for that base case for n equals 1, then our work just showed that it's going to work for k equals 2. And if it works for k equals 2, our work says it's going to work for the next term, so it'll work for k equals 3. So it'll work for every other value for n that you can think of.